In this video, we're going to cover how light interacts with atoms. And there are two ways that light can interact with atoms. The first way we call an absorption spectrum, which just means if I take a light source, a continuous light source, and I shine it through a cold gas, so that means that all of the atoms in the gas are in the lowest energy state, and then I disperse the light that comes out and I collect it, what I see is a smear of color with dark lines in it, right? The light bulb, the source, produced the smear of color, but after I shine it through the gas, I've removed some light and made dark spaces. And one of the first places we actually noticed this was in looking at the sun. So we call them the Fraunhofer lines on the solar spectrum, and astronomers will actually use them to calibrate telescopes. And those lines Fraunhofer gave different letters to. And again, if this is the sun that puts out a continuous spectrum, the lines seem to be dispersed throughout it. There's some removal of light from that continuous smear. And what's going on there is, remember that the sun is a cloudy ball of gas, and so that gas is composed of atoms. The sun is putting out continuous light, but the atoms in the solar atmosphere are absorbing some of it and leading to these lines, leading to these dark spaces. The flip side of that is what we call an emission spectrum. With absorption spectra, remember that we have a continuous smear interrupted by dark lines, and that's because we start with a cold gas where all of the atoms are in their lowest energy state. Here, we take a sample, like hydrogen, and we use excitation, heat or electricity, to get the atoms excited, so into a higher energy state. What that means is that they eventually give off light, and we use a prism to disperse it, and then we collect that light. And what we get is a dark background with bright lines on it. Every element has a unique absorption spectrum and a unique emission spectrum, so this is just those spectra superimposed onto the periodic table, right? Some of them, like some of these transition metals, are really complex. Some of them, like sodium, are pretty simple. And that's actually a way that we can identify elements, is based off of their emission spectra or their absorption spectra. The other thing about absorption and emission is that they're complementary. So if I have the same element and I look at its absorption spectrum and its emission spectrum, the dark lines in absorption line up with the bright spots in emission. That will always be true. Absorption and emission complement each other. And so there seems to be something going on in the atom that could be expressed as absorption and emission. Let's look closer at hydrogen. And the thing I want you to know is that this happens not just in the visible, right? It's not just light I can see, but I also get lines in the ultraviolet. I can collect the ultraviolet light that comes out of excited hydrogen, or I could collect the infrared light that comes out of hydrogen, as well as the visible light. And each spectral region just has a different series name, Lyman, Balmer, Paschen, based on the person who measured them. But the important thing is that they're all discrete lines. So what that means is that somewhere inside the atom, we don't have continuous transitions. Atoms don't give off a smear of light. They're giving off light only in specific places. And we need to figure out why. Before I leave this slide, the last thing that I want you to know, because it's something that drives me a little bit nuts, is that when I'm talking about this, I'm talking about the emission spectrum. That's the singular. There's one emission spectrum. If I had hydrogen and lithium, it would be their emission spectra. Right? So plural is spectra. There's no such thing as the word spectrums, so please don't use that. Spectrum or spectra. And so when scientists see interesting things like this, a regular pattern of lines on dark spaces, or a regular pattern of dark spaces on light, their automatic question is to try and figure out why. And the Rydberg equation, so Johannes Rydberg was a Swiss school teacher in the 1880s, and he figured out that he could predict the wavelength of any one of these lines, any one of those 5 lines, any one of the lines in the UV, any line in the IR. He could predict it using a constant, and that constant he figured out last, and also some positive integers. And if I'm talking about emission, this N1 has to be a smaller number. Why? So that if I subtract 1 over, say, 1 squared from 1 over 2 squared, I get a positive number here. The goal is always to have a positive emission wavelength. So you do what you need to do to get a positive number. And it turns out for Rydberg that it works for absorption lines and emission lines. Makes sense. They were complementary anyway. This is also an empirical model. That means that it's from data only. Rydberg took the data and he simply found that if he gave arbitrary integers, 1, 2, 3, 4, etc., to 1 and 2, he could figure out where the lines would be. He's not saying anything about the structure of the atom. That came later. He only said that I have an equation and it works. And the other thing to note is that higher energy lines, right? Higher energy means lower wavelength. They get closer together, so they start cramming together at the short wavelength side. That's because of the square relationship. If you think about it, 1 over a square will constantly get smaller and smaller and smaller. Here's how we use the Rydberg equation. So this is something that Rydberg might have done when he was first analyzing information. One of these lines turns out to have an n1 equals 2 and an n2 equals 6. And the question is, which one of these 5 lines is it? So what do we know? We know the n1, so we're going to put that in for our first fraction, 1 over 2 squared. We know that our second line is 6, so we're going to put that in our second place in the equation. And then we'll plug in Rydberg's constant. And what we're missing is the wavelength, or 1 over the wavelength is what we'll solve for. Right? Again, when I solve for this, I get a positive number. If you are plugging in numbers here and you end up with something negative, just switch the order here, right? Wavelengths will always be positive. And so we come up with a 1 over lambda. This is not the wavelength. You notice that this is very, very, very large, and it's also in inverse meters. Wavelength should be in meters, nanometers, etc. So if I want lambda, and I have reciprocal of lambda, then I really just flip that over. So I take the reciprocal of this number. I get 4.1 times 10 to the negative 7 meters, 410. So it turns out that this purple line right here is the one that Rydberg said had a transition between a 2 and a 6. Those are the arbitrary numbers he assigned. Again, not saying anything about atomic structure at this point. That comes later. Here's another one I could do. Right, and in this problem, Rydberg assigned a 2 to this value, and he was looking for the other n number that would correspond to this line. So what do? Well, the first thing that we do is we take nanometers and convert them to meters, right? This equation will not work unless your lambda, your wavelength, is in meters. It has to match the units of R. And so we plug in that, we plug in the 2 that we know, and we go through some math, right? This turns out to be 1 over this divided by that, so I'm just isolating the subtraction problem. And once I get through that math, I find out that this n2 value is equal to 4. And so I can solve for a missing wavelength as well.